Hello everyone. Today I will be sharing the topic of RISC generalized minimally recyclable component A, bank, try. To help you better understand, first let me introduce this component with an example. Here is a link to our current component on Git. Of course, this component has already been integrated into one of our software packages. As long as it's any of our Riva or RISC platforms, you can add this package through our package manager directly to your project and start using it without any additional configuration steps. So what is the function call station? Before we talk about the iBank component, we need to understand this concept. Let's look at this interface in the debugging process during our RT Studio 6 session. We usually step through several times for each step. After entering this command, our program will jump to a very deep place. So when we look at this, on the left side of the IDE, this left side will show us every level, which means from each level of functions. The jumping process. We started from the main function MMF inside. We kept jumping up one level after another until we reached our current function now. So the function call station is a way of showing the relationship between function calls when a program reaches a certain point. This is a forward process where we start at our initial breakpoint in this main function and run step by step until we reach our current function, showcasing the entire process of debugging that function. What about backtracing? Backtracing involves finding the instruction for the previous function jumped from the currently executed instruction, continuing until it finds the entry function of our running program. For user-specified functions, what users need are the names of the functions corresponding to the jumps and instructions. This allows us to reverse engineer the calling relationships of our functions. So the function call station shows the forward calling relationships of functions. Backtracing then shows the reverse debugging relationships of functions. Generally, in our firmware described as text, there is no information on function names. Usually, software can output the function pointer of the called function. With these function pointers, we can use tools on our PC and to search through the most comprehensive EF format file. To find the address function pointer, which corresponds to the name of the function associated with the number, and then display the name of the called function in reverse order. As for done, it provides a tool called address to live. So this tool is in the same directory as the G3C compilation tool. Users can find one of these tools under the roadbed of their own toolchain installation. For example, if we press this toolchain with its name, it's just this press. Each of these butlers has a different name. Generally speaking, in this case, we are probably the first one under one of our installation packages. So, what kind of component is a bank try? Second, in the case of bank choice, it only provides one user NPI, which is one of our bank try components. As for this function, for users, it can be used in places where recycling is needed. Phishing, the PI will be in this. For example, if you use prettyf, you will use prettyf to reverse output an address of the phishing function. Then we output these addresses, and then use the address to live tool, which is the one we just explained. We can use one of our functions, one dispatch station, and the reverse one. Then we can also assign this API to an API of an assertion in the current system, or in other words, a volume of sound field processing functions. So, speaking of this, we can understand. As for a bank try, the purpose of this component, or any other bank component, is to help us through some means. Moving us from the current system execution to this position, reversing our function call station, it will be a process of calling a function as a whole. By printing it out, let us manually know these functions, starting from the position where we execute one of our station cycles. What exactly happened? What kind of function research relationship did we go through? Then through this information, we can assist ourselves in doing some things. Debugging and such information assist us in conducting a debugging class of information. Boss Mel, let's do some debugging. So, let's use this in RTS Studio to illustrate how to use it. Apple will first explain how to use our attack tool rectangle. After we open our RDO, as long as we are using a VB platform, then we can search for AIC in our software package management. Then, in the PA, after we turn on our pair option, after turning it on, we add icons, cards, and and we can add our components to one of our systems. Perform a compilation. So, in most cases, sometimes we don't provide these two symbols for a link to join our system. This is because our components default to using this software in a convenient way, which means we don't need any configuration at all. Just directly load the software report into one of ours. In this web platform, inside this, we can directly call our station loop component to perform a station loop. So usually this is accurate, this. If we use this method, we rely on one of these two symbols. These two symbols are the starting segment and the ending segment of a code segment, the two addresses. Then we need to add these two symbols at the start and end of a code segment in our link script. After adding them, it will become like this. Once you add this component, it can be used normally. This is our default method. Let's take a look. After adding this component, when we call several functions during the process, at the deepest level of one function, where it gets called, we use R. API provided by the bank tried to allocate memory. We can see that it prints out each level's PC value, as well as the values in the RAPE section, along with the range of each function education station. Ultimately, we provide R. Add pointer to live tool with a real command. Then we copy this command into our command letter. After copying it, we can use this tool to print out the name of the function corresponding to our address. In this way, through a reverse engineering process, we can output our function calling relationship. Let's take a look. This is the current diagram that we have created using our tool to export the data from it. This war has been exported, and then another output has been made by the C number coach. At first, we see the current C number transaction being exported, followed immediately by the function call for occupation of external task. The previous section's U function was optimized in the upper level self function, which kept increasing until it reached the entry point function for selling the city as part of reality. We can use attry to print out the entire C number trading process. Next, let's introduce the principle behind the bank component's efficiency. First, we press the bank component, which provides an API, and then there is the API at the back. By default, the software sends the result back directly to the user, who can use it within the logic or in the autos environment. It supports any kind of RISC 32-bit and 64-bit systems. There are caches here where you can use them. Then, whenever we want to perform recycling again, we just need to use R. With our fishing and nurturing API, we can directly print out our corresponding C-beam, the functions of the fishing and nurturing station, the scope of the strategic competition war of the fishing and transportation station, as well as our PC values. Then you can also output our ID points. The ID to live tool supports multiple commands. Then we can use this tool to print out the corresponding name and function name of one of our function troop stations, and perform an analysis for us. Instead, it supports two types of brought-back components. The hardware implementation method, which means relying on the edge parameters of compute 3, relies on the edge parameters we have at the back. The side spectrum at the back is actually easier to remember when you enter it, which means we look at of, which means to ignore. This omission means no, which means no, no. So, adding this parameter means not to ignore or not to ignore. Then this method will occupy a helpless imported machine P, but the combat recovery code is relatively simple in real lines. There will be an advantage of this memory saving function. That is to say, if we add this up parameter, then during the system compilation process, one of the systems is the FP system storage, and it will be occupied and will not be used as another method. So at this point, our system, for example, if we assume by default, if the default is exactly the one that has been reshaped, if it's a memory counter, then it defaults to 32 basics. If we use it in this way, then one of them will be occupied by and can only use the other 31 layer counters. In this way, then another way of reflection is how our software implements it, which is more standardized according to the refunction call. We can just use the convenient reverse commands, search functions, call a pointer to the squatting station, call a pointer to the squatting battle pointer, and the function being adjusted. This is a brief introduction to the two methods we have implemented. Well, to sum it up, it's just that. Regarding our hardware testing method, one of us, is finding this war, FP. This advancement point is directed at one of our stations. So, the certificate pointing to the dead of the station manager is us. After compiling for us, after the compilation is completed, it takes up a storage space to do this thing. So if the software implementation method is that we don't have a storage device to save our a war pointer, then we need one. Then we need to know the instruction pointed to by the previous function from the current situation. Sequentially, one by one, follow the functional command to adjust according to the function operation specification. Directly until you find one that conforms to the function call specification, which is the command for adjusting our war, and then immediately find our I. We can gradually find such a value for one of our machines, so that we can level up step by step. Found one of our the reverse one, the convenient one, found a function called function dispatch station of ours. So first, let me introduce a principle of hardware implementation. We can take a look at the hardware reality method. It depends on the FP proximity of this kernel. When editing, you need to add this side edit parameter, which means not ignoring this. Well, if we don't ignore this war baseline, then this stratum line will operate the war feed line during the compilation process. Once the above parameters are enabled, this secondary calculator base will also be our X8, and this baseline will not be used as a regular base group. Next, we need to, first, build three concepts. This concept and the three important entrants are war, and war is about preservation. Fishing for the root function at an expense within the function. It is the function from the previous season. The war and function return address of the function from the previous season are stored here. If it's a terminal function, it won't make a single call. So if we don't call it, it won't save the return address of this function. It will only save one war at the function. The RA level total is the function return address to the initiator. After the function branch is called and completed, the return address is saved in this initiator. Another thing is our SP, the squat load pointer initiator, which handles both inbound and neutral operations. It's the value of a basic operation, which is the value of the P-calculated storage protection. So it points to our station. The Facebook programmer is a war pointer accelerator. Yes, it is a counterpart of the temporary top importer, so it's just that. The current initial direction of the CDEP points towards a base station for our war. This is our concept, three main lock-in processes. Let's take our Vs2 as an example and A as another example. Let's look at how it calls its functions during this process. If it uses our F-leveling method, what does the calling process look like? On the left side, we have an example code, which is a brief code. On the left side, we can see that in the main function, we called the function insertion 1 inside the insert1 function, we called ABCD. This function goes through three levels of recursion. Now on the right side, we are doing a reverse operation. Let's see how it calls itself. In the reverse process, we can see that first step is to adjust our war, then from our RA. Save it into our station, then back to our zero value, which is the VIS input value saved into our station. Next, we will reassign our zero value again, which is our current VIS layer line. We can see that each time after a function call, each time when the CDEP recurses once, his behavior remains consistent until the last time, where it doesn't save the RA because by the last time, it won't be the final level function, which is our end function. It won't have a recursion down to the next level, so it doesn't need to use the pure calculator values. When we look at each call, every level of function call processes all the same except for the last one, which is slightly different. So why are they all the same? Because during their fishing process, they follow our RV function specifications. Then we can follow this rule, reverse it, reverse from the current position of reverse and take one of ours. Let's perform a reverse inversion of our this war. We can take a look. First we'll start the bridge test, our current bridge test. At the beginning, our SP, and also FP, such a value. So from now on, let's look at what my Han said. If he wants to jump to the three gods, Let's see what it looks like now. So, if it were to jump to Fanxing E for execution, what kind of process would it go through? We can see that it will continue to go down, and then open up another one, part of it, a war, and then open up another part of the war. Let's look at the left side. Is there a war in this kind of political P screen? Then we can see that the part above is what a war in my mic function looks like. At the beginning, the first this byte, it's from the return value of which is an R. Another level down is to raise a battlefield, which is where our war FP level goes to FP, which is the position pointed to by FE. Then we start, for example, when we jump to the next section where the sound is ejaculated, another war has been waged, another level 1 war has been tightened. So, first of all, at the beginning of the C, we still placed our C advanced main weapon, and then we placed our MP technology FP. The value indicated is the same as the value at the bottom of the index. If I were to type out the last terminal function, let's see how this war unfolds. This war has been divided into such a few parts. So, when one of our functions is divided into several parts like this, what if we
if we want to find it, then if we want to perform an and then send it back, how would we find it? We can, for example, through the current function, through the current level of this war, we find the next through the value at its current position. Through the value at this position, we can, through the current war.
Let's go through this level of war. If we go through this level of war, then we can. Found it. At this location, find the next level of a war station. Then we start from this position and look down. The first position starts from RA, and the second position starts from FP. So, after I find this level of war and then find the FP, we can locate the location of the station for the next level of war. So, what do we point to from the station location? The first one is A, the second one is FP. So why is it so regular? Because the arrangement of all these 1S stations is standardized by the selected function dispatching station. That's how it's set up, that's how it's placed. After we found this thing, if we can see that we have found it through FP level by level, we have found one of the previous level stations. Then we can solve it to find its RA, where R points to the next which is the execution of the command that jumps after executing the current function, and the next one returns with the command that needs to be executed. Through RA, we can find out what we are doing. The function from the previous level, the jump function, the jump address, then I can do it. If we find the name of a function, we can invert it to our PC value. Then, through this address, we will find the name of the corresponding function. The above is a brief introduction to the principle of our hardware. Next, we will briefly introduce a method and a principle of our software. We also called a template, and we repeatedly mentioned it in reverse. We even used a template to describe how the subfunctions of negative functions edit their connections. The agreement on the transportation relationship between rich functions and child functions, such as the layout of debts, parameter passing, etc. So the edited program follow the rules and there are traces to follow, then follow the view that there are traces to follow. So the analogy is that when we also don't use this sound change parameter, one by one the result of editing, we see that this edit supervision does not store one of ours. It's just that there's no operation on our 1SP. For example, some parts are not operated on our 1P. This process, but right after operating the station, they will all operate our 1R, have operated this certain basic device, and such an behavior. So if we go through this command, it means we go through them one by one in parallel. We can first find the command above, and then proceed. Then immediately find the following command. So we can use the following command to find our function. When it reaches this point, its PC value before the function call can be known. We need to know the size of the upper level function stack. Then we can step through each level using convenient commands to trace the process of a function call. From the above function's return edge code, we can see that the strategic operations and return address operations are consistent in behavior, both for the team and individually. The conclusion is that the operational behavior of the instruction station is fixed. After completing the operation at the station, it will take the return address and save it as a calculator value into a state-saving area. Based on the function teaching specifications, we can reverse engineer every instruction to find out the range of each level's war, thus determining the scope of each level. the pointer to the called function, suddenly identified by our IDD tool or other debugging tools like Jennings iTool. It will reveal the name of our function. Since the function reverses from the current P3 values to search for instructions that meet the requirements and modify the war instructions. Based on the war, according to the parameter of the instruction, calculate the size of the war. Then modify the war command's adjustment command to save the value of register I in the war. The RA register stores function jump transmission commands. According to it, you can reverse engineer PC. The following decimal equation is a function that represents the entry point for our overall software implementation process using the aforementioned method. It is also this function, which is the core of the software return mechanism within our entire software package. If anyone is interested in this temporary return mechanism, you can look at the experimental way of the software and see how this function is implemented. Thank you all. My speech is finished. Hello everyone.